Hi everyone, so welcome to a new talk on the Shannon channel. I'm really happy to have today Murat Kocaoglu from MIT IBM AI Watson Lab, and he's going to talk about entropic methods for causal discovery. So Murat, we're very interested and going to listen to your talk.
Thank you, Salim. So thank you for giving me the platform as well. So let me just start sharing my screen. Okay, so you guys can see it, right?
Yes. Yes.
Okay, awesome. So I'll just start. As Salim mentioned, my name is Murat Kocaoglu. Thank you for coming to listen to the talk. And the title of my talk is Entropic Methods for Causal Inference. And this talk is basically based on joint works with my PhD advisors, Alex Dimakis and Shriram Vishwanath, and also my collaborators, Sanjay Shakotai, Konstantin Karamanis, and Baba Kasibi. Okay, so this is an outline of the talk. First, I will start talking about a big introduction to Pearlian causality, give the necessary background for the rest of the talk. And then I will move to the first contribution, which is basically when you have two variables, can you infer the causal direction if you don't have any latent variables between them? And then finally, I will move to the last part, which is basically the similar setup, but now you have a latent variable, and can you still distinguish between different causal graphs? So let me start with the background section. This is going to be very fast, but feel free to stop me if something is not clear. Okay, so causal models are used to model the mechanism between random variables. So they are used to represent the underlying system. And the main assumption within the Pearlian approach is that we assume that the set of causal relations between random variables can be represented by a directed acyclic graph. So the graph here you see on the right-hand side is a directed acyclic graph, and this graph is going to be called the causal graph of the underlying system. Okay, so but what does it mean when I say that a variable x causes another variable y? Right, so let's try to understand this with an example. Consider the following system at hand. Suppose we are having an exam, and this girl is actually participating, and then let me call her answer to a particular exam question as variable x. Okay, suppose x is realized, sampled as lowercase x. Now, if the underlying system is as depicted here, then the variable y, which is the answer of the girl on the right-hand side, is going to be realized conditioned on the value of x. Right? So this basically tells me there's a clear causal connection between random variables x and y here. So first, x is realized, and the variable y is realized given the value of x. Okay. But when you see, so when you don't see the time aspect of this, and when you just see two variables x and y, how can you actually see this asymmetry between random variables? So from the data, it's not going to be possible. But one thing to understand is basically you can perform an experiment, which is also called an intervention. So let me define the intervention in this case as follows. Suppose I talk to the teacher, and then I tell her to go and tell the girl on the left-hand side the answer to the question. Right? So I send her to the left, and she tells the answer, and then the girl writes it down. So the value of x is forced to take a certain value. Right? So then based on this, because of the underlying system, underlying causal mechanism, the value of y will be realized depending on that, and it will be set to the answer as well, right? However, if I actually ask the teacher to go help the girl on the right-hand side, right, the value of y will change, but because of the underlying system, the value of x will not change, right? The value of x remains the same. It has the same distribution. So this is actually how you can actually see the underlying asymmetry between random variables when you have a causal system. Only after performing an intervention, you will see the effect, the causal effect. Okay, so this was a simple example, but let's take a more realistic case. So suppose I'm given a data set of two binary variables.
I have maybe a very early question. So how, maybe I missed the argument. So how did you prove that, how could you tell that x caused y and the way you explained it?
So I will explain a bit more later in with other examples, but what I said is the following. When you force a value on x, then this affects the distribution of y.
Yes, yeah, true.
But if you force a value on y, this doesn't affect the distribution of x because of how the underlying system works, right?
Okay.
So that is an asymmetric relation there. So that you can, if you could observe that, then you would be able to distinguish, say that x is causing y, not the other way around, right?
Okay.
Yeah. So that's the basic idea. And let's take this example. Here, S is a binary variable that stands for whether the subject is a heavy smoker or not, and C stands for whether the subject gets lung cancer before they turn 60. Now, how do we check if these two variables are causally related, right? So there may be multiple causal explanations of the correlation that I observe. So the first and simplest explanation is smoking indeed causes cancer, and this can induce some dependence that I can observe, right? But a more intricate explanation can be that maybe there's a gene out there that may be active, and then that gene may make me crave nicotine, hence causes me to smoke, but the same gene also gives me cancer, right? Then this can also induce the observed correlation between smoking and cancer. So now suppose I want to distinguish these two causal graphs from one another. Which one is the true one? Okay, here is how I should check this. I should basically find 100 people, and I should force them to smoke. And I should collect data on whether they get cancer or not. And then I should find 100 other people, and I should force them not to smoke and collect additional data. Now, if I see different cancer rates between these two subpopulations, then I can say smoking causes cancer. Okay, so what I just described here is nothing but a randomized experiment, which has been used in clinical trials for decades. But in this context, it's also known as an intervention. So here, an intervention or a randomized experiment helped us understand the causal relation. But how did it help us understand? So let's see how a randomized experiment helps in the language of directed acyclic graphs. Okay. So before the intervention, we had two possible causal graphs, left or right? Now, after the intervention, since I'm forcing the value of smoking variable, effectively, I'm cutting off the connection between gene and smoking variable here, and then observing data from that. And in that, after I cut the edge, smoking and cancer become independent, as you can see. Okay. But whereas if I intervene on smoking, and if the true graph is the one on the right-hand side, then intervening on smoking will not change the dependence, and then I will still see a correlation between smoking and cancer. Okay, this is how an intervention or a randomized experiment helps distinguish two causal graphs from one another. Okay, so, but we can see things from the other way around also. So maybe I cannot actually perform this experiment, because maybe forcing people to smoke is not ethical, which it's not, right? So if I cannot perform certain experiments, then if I have expert knowledge, and if I know the causal graph from expert knowledge, let's say, or through some other means, then without performing the experiment, I can actually predict what will happen if I perform the experiment. What I mean is, if I know which graph is the true causal graph, I can understand if I intervene on smoking, whether cancer rates will change or not. Right? So therefore, learning and knowing causal graphs can be very helpful in policy decision making. Okay. All right, so let's go into the details of causal modeling. So within the Pearlian regime, there's something called the structural causal models or structural equations. So here we have two variables, let's say, and x causes y, something I know. This comes with the following set of structural equations. X is sampled from some distribution P of x. E is sampled from some distribution P of e, which is independent from x, and it's a variable that I don't get to observe. So I'll call this e as an exogenous variable. It's not on the graph, but I know it affects my variable y. So y then can be written as a function of x and e together, where x and e are independent. Okay, so this is the general assumption. And in general, if you have a bigger graph, then you just say that, oh, the variable y is a function of its parent, set parent y, and an exogenous noise e, which is again independent from all the parents. So this is the typical assumption for using structural equations. And now let's try to understand what happens if I intervene and sample linear distribution. So here you see the causal graph on the left-hand side alongside with the structural equations that come with it. And then suppose I perform an intervention on y, which basically means setting the value of y to something, right? Forcing it to take lowercase y. Then all I need to do on the structural equation is basically replace wherever I see variable y with the realization of y. So therefore, first of all, the causal graph changes in the sense that y no longer depends on x, but is set by the value I decide. Right, so the causal graph now is the one on the right-hand side, and the structural equations change as given. And these structural equations now induce another joint distribution on the random variables, which is what I'm going to be sampling from if I perform this intervention, this experiment. Okay, so this is how an intervention distribution looks like. All right, so but structural causal models are not the only thing to represent causal relations. There is something called Causal Bayesian Networks, which is a less detailed description. So Causal Bayesian Networks are basically a directed acyclic graph, which is the causal graph, alongside with a joint distribution that factorizes with respect to this graph. Okay, so just from these two, you can actually calculate the interventional distributions by using the factorization formula and using the causal graph, okay? Assuming that there are no latent variables. All right, so this is a very, very fast introduction to causal modeling within the Pearlian regime. So now let's come to the question we want to ask. Suppose I want to learn causal graphs, right? How can I learn a causal graph, let's say from data itself? So one thing I can try is I can try to learn the corresponding Bayesian network, the dependency structure, right? But the Bayesian networks are not unique. So if I see two variables, x and y, and I know one of them causes the other, then both Bayesian networks, x into y and y into x, can encode the observed joint distribution. Therefore, I cannot distinguish which one is the true causal graph just by learning the Bayesian network. Okay, so it's not unique. There are two main threads using which you can actually learn the underlying causal graph. The first one is what we actually explained, that you can actually use interventions, right? You can perform an intervention and then collect additional data and see how the distribution changes and use it to reconstruct the underlying graph. That's a thread by itself. And the second thread is in the case where you cannot actually perform intervention, maybe there are some additional assumptions that you can put on the generative model, apart from the Pearlian assumptions, using which you can actually infer the true causal graph. So this is what we call data-driven causality, and this is going to be the main focus of the rest of the talk. Okay, so that's all I have for the background section. If there is any question, I can take it. If not, I'll just move on to this next section.
Yeah, I think there is no question so far.
Okay, great. So the next section is entropic causal inference without latent variables. So here is the setup. Suppose I have two variables, and each of these variables have n states. So these are discrete, and they can also be categorical variables. I'm given the joint distribution between them, which is nothing but an n by n table in this case. Okay. So now I'm saying, suppose that one of the causal graphs is true, either x causes y or y causes x. Okay. How can I learn this? We are putting the following assumption. Suppose that the ray entropy in the true causal direction is small. So whatever the true causal model is, its ray entropy is small. So I'm going to explain how you measure the entropy of a model in a minute. But then the main question we're asking is the following. Is it true then that for all possible reverse explanations that are in the wrong causal direction, I need large ray entropy? Okay. So if this claim is true, or if this statement is true, then I can use this entropy as a measure to induce some asymmetry, to observe some asymmetry between directions, and then tell apart which causal graph is the true causal graph, right? So the rest of the talk, including this and next section, will be a variation of this question and understanding whether it's true or not under certain conditions. Okay, so how do you measure the ray entropy or amount of randomness of a model? So if we look at the model on the left-hand side, x causes y, the only sources of randomness are x and e, because y is a deterministic function of x and e. And I know x and e are independent, therefore their entropy should be additive. So the complexity or the amount of randomness that I need on the left-hand side is going to be h of x plus h of e. Okay. Versus on the right-hand side, it's going to be h of y plus h of e prime. So here e and e prime are the exogenous variables that I don't get to observe. Okay. So after calculating these things, I'm going to say that the direction that admits smaller entropy should be the true direction. So that's how the algorithm will go. And in the case where I use ray entropy of order 0, which is nothing but the support size or the cardinality of the random variable, I will have an identifiability theorem. And then in the case where I use Shannon Entropy, I'll have a conjecture and an algorithmic approach to handle this.
Murat, I have a quick question. So
yeah.
If I take a simple case where you have from communication, where this is a like an additive white Gaussian noise. So y is equal to x plus e. Let's suppose e is the noise.
Yeah.
And both direction would have the. I'm guessing. Maybe I'm wrong, but would
yeah. So I finish your question. I got the question, but yeah, I'll let you finish.
So wouldn't both model have the same Rayleigh entropy, and how would you be able to tell?
No, so the thing is that when you try to fit in the reverse, so what you're talking about is the additive noise models.
Yes, yeah.
And additive noise models there are actually proofs that for most of those additive noise models, you will be able to identify the true structure. And the key observation here is sorry?
Would or would not be able?
You would be able to. You would be able to. And the key observation is the following. So you can fit an E prime in the reverse direction, but that E prime will not be independent from Y. So that's the key constraint, that you can always construct an E prime, you can always fit both directions, but it's simple enough, I mean, at least in my case, let's say simple enough E prime will not be independent from Y, that's the hope. But additive noise models use a slightly different approach, but yes.
If Y equal to X plus E, then X is Y minus E, and E is independent of Y. Yeah, but maybe I should think about it offline. Like,
oh, I see. If there is no function on X, I see, then it's perfect symmetry. Yes, that case, I guess, is not identifiable. So additive noise models require either none. Yes, okay, good point. So additive noise models require either the function on X to be nonlinear or the additive noise to be non-Gaussian. I think that was the...
Oh, okay.
So yeah, if either of them is not true, then you cannot actually identify. So you are right. Yeah, you're right.
Okay, thanks.
Yeah. But remember, this is the discrete setup where addition is, I mean, you should talk about like modular addition in that case. And I'm not really going in that direction. This is going to be a different approach.
Okay.
Okay. Yeah. So let's see the formal statement of the theorem for when I use cardinality of the random variable as a measure of its complexity. So suppose X causes Y. Okay, this is the true direction. And let the distributions of X and E be sampled uniformly randomly from the corresponding dimensional simplex. So simplex is basically the polytope where every point on that polytope is basically a distribution, right? So I'm going to sample distributions uniformly randomly. Now I'm also going to put an assumption that F is generic. So this is a bit complicated to explain, so I'm not going to explain it here. But the important thing is that if you randomly sample a function among all discrete mappings, then it will be generic with high probability, so you can show that. So it's not a very strict assumption. Under these two assumptions, then we can show that any valid causal model for the reverse direction requires an exogenous variable E prime that has cardinality at least order n square with probability 1. Okay, so what this means is that if you try to fit in the wrong causal direction, and if you try to reconstruct an E prime, that E prime will always have large cardinality, order n square, with probability 1. Okay, so of course there's an adversarial set, but that set has measure 0. So based on this, we have the following corollary that if in the true direction, exogenous variable has cardinality less than order n square, then the causal direction is identifiable because of the separation. Okay, so this is the main result for when you use cardinality as a measure of the variable's complexity. Okay, is this clear so far?
Yes.
Okay, great. All right, so, but in practice, I don't really want to use cardinality of the variable as a measure. So why is that? One reason for this is that, so typically I'm going to predict or estimate the probability distributions from finitely many samples, right? And then you can think of this estimation as like, instead of observing the actual values, I will observe a perturbed version of these probability values. But if I use perturbed versions, then even in the true direction, the cardinality that I need will be order n squared. So even if the assumption is true in real life, that the cardinality is actually small in the true direction, when I estimate it, it will be high in both directions. So this is not going to be a stable metric with respect to finite samples. Therefore, we want to use Shannon entropy, and hopefully we want to say something similar in that case. But the problem is that it's much harder to prove things when you use Shannon entropy, and we only have a conjecture for this case. So I'm not going to state the explicit form, but it basically says the same thing, that if in the true direction, exogenous variable has small entropy, then in the reverse direction, it shouldn't have small entropy, and you can actually use this. Okay. Okay, so assuming that the conjecture is correct, now we want to use this in practice. So we need an algorithmic approach to handle this. What is the question that we need to solve? It's the following. So again, suppose I'm given the joint distribution P of x, y, and now I'm trying to fit in the one direction, y causes x. Right? This requires me to discover a g, a function g, and a distribution, a random variable e prime that is independent from y. Okay. Then I need to find e prime with minimum entropy that fits onto the observed joint distribution. So now at this point, you may be thinking that maybe entropy of e prime is actually similar to the conditional entropy because that's the remaining amount of randomness when I condition, right? But you can show that it's a fundamentally different quantity, and it's actually NP hard to compute h of e prime exactly. Okay, so it's actually a hard task, but we are going to have a characterizing lemma for this. So I'm going to define the following random variables.
What are the bounds on the alphabet? I mean, is the hardness coming from the alphabet being?
Hardness is coming from the cardinalities of x and y being n.
Okay.
In that n, it's yeah, it's not. You can't find a polynomial time algorithm.
So we're talking about still discrete alphabets here.
Yeah, everything is discrete throughout the talk. Everything is discrete.
Okay.
Mm-hmm.
And still, it's NP hard to.
Yeah. Yeah. In fact, it's even a simpler problem is NP hard. So I'll show it in the next slide.
Oh, okay.
Yeah. So this is a lemma that characterizes entropy of E prime. So as I was saying, let's define the random variables U sub I as those discrete variables which have the same distribution as the conditional of X given Y equals I. So for every value of Y, I'm conditioning, and I'm looking at distribution of X. And this gives me a bunch of distributions, U1, U2, up to UN, right? We can show that the entropy of E prime is actually lower bounded by the joint entropy of these newly constructed random variables, U1, U2, UN, okay? So then you can also show that this lower bound is achievable, which basically means that whatever problem we were trying to solve, minimum entropy exogenous variable problem, is equivalent to the following problem, which is called minimum entropy coupling problem. I'm given n distributions and marginal distributions, and I'm asking, find me the joint distribution among them that has minimum entropy and marginalizes to observed marginals. So this problem is equivalent to finding the exogenous variable with minimum entropy. Okay, and we know that this problem is NP hard even if you have two distributions, right? And in my case, I will have n distributions, each with n states, because each of these marginals come from by me conditioning on Y equals I for every value of I, and each of those has n states. Okay, is everything clear so far? If there's any question?
Yeah.
Okay.
It is clear, yes, thanks.
Okay, great. Yeah, so this is the problem that we need to solve, but this is NP hard, so we don't know how to solve this, but we have agreed that, okay, before that, you can try to solve it, but the problem is that you will need end-to-end optimization variables. So even if you try to do gradient descent, it's not going to be easy to approach it this way. So then we have a greedy algorithm to solve this problem, and it's a simple algorithm, and it runs efficiently, and you can also show that the output of this algorithm is always going to be a local optimum of your loss function. Okay, so I need to mention at this point that we were very recently informed that the same algorithm was discovered by Pinsky et al. In 2013, and check out their paper. It's a different application, but they came up with the exact same algorithm for their approach. So let me try to explain how the algorithm works and the motivation behind it. Okay, so remember, my problem is to construct a joint distribution between two variables that has minimum entropy and marginalizes to the observed marginals, right? So here, let's say I have two distributions. Here you see one column, and here you see one row. And I'm trying to construct a joint, which is this matrix, that sums and column sums are going to give me this distribution, and row sums are going to give me this distribution, right? And I want it to have minimum entropy. So the key observation we made here is this, that if you have a probability mass of P, its contribution to entropy will only increase when you break it down into smaller chunks. Okay, and if I'm trying to minimize entropy, then the useful thing to do is maybe I need to keep large probability masses intact. I don't want to break them apart. And this is exactly how the algorithm works. So we basically take the maximum probability mass that we can take and put it into the table, and then update the marginals, and then we repeat this process. Okay. So this algorithm is guaranteed to terminate in finite number of steps, and it will give you a valid joint distribution. So this is the algorithm. Okay, so this was the algorithm for solving the minimum entropy coupling problem, which is what we need to solve the minimum exogenous variable problem. Okay, so now taking one step back, let's look at the whole framework. So given P of xy, if I want to predict whether x causes y or y causes x, under the assumption that exogenous variable has small entropy, I will do the following. I will estimate the conditionals P of y given x and P of x given y. Then I will fit the causal model with minimum entropy in both directions. I'm going to use P of y given x to fit the model where x causes y using the minimum entropy coupling algorithm, and then do vice versa for the other direction. And then I will pick the causal graph with smaller entropy to be the true causal graph. So this is the high-level approach. And finally, we tried this on the benchmark Tubingen dataset. Tubingen dataset is basically this dataset of real cause-effect pairs where we think we know the true causal direction. And basically, the bottom line is that our algorithm performs very similar to additive noise models. And the point here is, takeaway here is that this dataset is very heterogeneous. There are real variables, valued variables, and discrete categorical variables. And additive noise models do not work for categorical variables. And hours work for this. So it seems like giving a similar performance in this heterogeneous data set shows that it's a promising approach. So that's the bottom line. And that's all I had for this part. And I'm going to spend most of the time in the last part. But if you have any questions at this point, this is a good time to take.
Yeah, I think, yeah.
Okay.
I think it's okay now. Yeah.
Okay, great. All right, so we have done the case where I have two observed variables and there is no latent variables, and I was trying to decide whether X causes Y or Y causes X. Now, we are going to assume there are latent variables in the system. So if you have a big graph and if you have latent variables, then there is some standard literature which says that you can use condition independence tests to still recover certain latent variables, the location of certain latent variables. But if you do not perform experiments or without any other assumptions, you cannot distinguish simple causal graphs. For example, you cannot tell apart these two causal graphs from one another. So, and this may be relevant in practical scenarios. For example, remember the case where I was trying to decide whether smoking causes cancer or not, right? So I can always think that there's a latent confounder between smoking and cancer, and that's something I cannot observe. And I know that cancer do not cause smoking. So then I'm asking the question whether smoking causes cancer or it's just due to a latent confounder, the connection that I see, the correlation that I see. Okay. So now we're asking the following question in parallel with the previous part of the talk. Can we distinguish these two causal graphs if I assume that the latent variable is simple? Okay. And for the purposes of this talk, I'm going to call the graph on the left-hand side as the triangle graph, and I'm going to call the graph on the right-hand side as the latent graph. Okay. So now assume that Z is simple with respect to some notion of simplicity. Then we have the following key observation. Most distributions P of xy that come from the triangle graph, the graph on the left-hand side, do not fit onto the latent graph with a simple enough Z. Okay. So when I say fit, this basically means that a P of xy fits onto latent graph if there exists a joint distribution Q x y z such that it marginalizes to P of xy and it induces the condition independence x is independent from y given z. Okay, so such P of xy's, I'm going to call that they can be fit onto latent graph. All right, so, and when I say simple, again, parallel to the previous part of the talk, I'm going to first consider the case where z has small cardinality, small support size, and then I'm going to consider the case when it has small entropy. Okay, so this is going to be the approach. Okay. Now, again, to remember the setup, and now suppose I'm assuming that the latent variable has small cardinality. That's the case. I'm given two variables, each with n states, and I have the P of xy. Now, suppose the true causal graph is z causes xy. Now, we are asking the question, how does such a causal graph manifests itself in the joint distribution over xy when z has small support size? Okay. So if I write the distribution P of xy and get it through marginalization on P of xyz, it's very easy to see that if I write this in the matrix form, then this P of xy matrix is nothing but a convex combination of k rank 1 matrices because of the condition independence that the graph induces. Okay, and I can rearrange these things, write the rank 1 matrices as outer products, and then rearrange rows and columns, and see that this is actually nothing but a non-negative matrix factorization, U sigma v. Okay. So I can also do the other direction. So I start from P of xy, it's a matrix M, and I find its NMF, which gives me U and V, which are non-negative terms, and I can do a row and column normalization to get U tilde sigma B tilde, and then you can show that these rows and columns of these matrices are going to be valid probability distributions, which means that they will correspond to a valid model decomposition, the decomposition of the joint distribution. Therefore, any NMF gives me a joint probability distribution over 3 variables for the given number of states for the latent variable. And based on the other characterization, there's any finite unique connection. So what I'm saying here is that given P of xy, if I want to search over all model decompositions or all joint distributions on Q x y z, I just need to search over all non-negative matrix factorizations, and I'm going to be done. Okay. All right. So now remember, our objective was to distinguish these two causal graphs. Now, based on what I just talked about, on the left-hand side, if the true graph is the latent graph, then the joint distribution matrix P of xy has non-negative rank, which is upper bounded by the support size of C, cardinality of C. On the right-hand side, we have the following theorem. Again, we are using the same sampling method. Suppose each conditional distribution in this triangle graph is sampled uniformly randomly from the corresponding dimensional simplices. Then the P of xy matrix is going to have a non-negative rank of n with probability 1. Okay. So this basically says that in the wrong causal graph, the latent variable that you construct, because of the connection between NMF and latent variables, right? The latent variable you will construct will have cardinality of n with probability 1. So combining this with the assumption that the cardinality of the latent confounder in the true causal graph is less than n, we get the following corollary that if we have an algorithm that can construct the minimum cardinality z, which is nothing but the non-negative rank of the matrix, right? Then we can distinguish latent graph from the triangle graph. So this is using the cardinality of the latent variable as a measure of its complexity and saying that reverse direction you cannot fit, so you can actually tell apart these causal graphs from one another. Okay, this is the part where you use support size. So any questions up to this point?
No, no questions.
Okay, great. All right, so this is fine, but maybe I'm not really happy with this result. And the reason can be the following. So I observe x and y, and both of them has n, cardinality of n, right? Support size of n. And now I have to put a restriction that, oh, latent variable must have cardinality at most strictly less than n also for me to be able to distinguish, right? But maybe that's too strict for my purposes. So then the hope is that maybe I can use entropy of the latent variable and limit that instead of its cardinality. And even though it has large cardinality, if it has small enough entropy, maybe I can still distinguish these two causal graphs. So that's going to be more interesting direction, I think. So that's what we're asking in the rest of the talk. Okay, so again, to remember, we are given P of xy. And now let's assume that there is an algorithm that can construct a z prime with minimum entropy in the latent graph. This basically means that this algorithm constructs a q xyz prime that marginalizes to P of xy and satisfies the condition dependence constraint I have in the latent graph, right? If the true graph is the latent graph for some z, for some latent variable z, then this algorithm will find a z prime with entropy upper bounded by h of z. Why? Because it will always find z itself, but it may find something even better, something even with less entropy. Right? So h of z prime is upper bounded by h of z in this case. Now we're asking the following question: if the true graph is the triangle graph, then does this algorithm still find a z prime with upper bounded entropy, with entropy less than h of z? So notice that the fraction of models where this algorithm finds such a z prime is exactly the fraction of models that are not identifiable using this entropic approach. Because if algorithm can find such a z prime, if there exists such a z prime, then I cannot use h of z prime to separate these two graphs. Whereas if it cannot find it, if h of z prime is always lower bounded by h of z, then I can use h of z as a way to threshold and identify which graph is the true causal graph, right? Okay. So again, I'm sampling P of xy from the triangle graph, and I'm asking if there exists a simple enough z prime that makes them independent, right? So in the case of binary variables, binary observed variables x and y, we have the following theorem that says the causal direction is identifiable in the limit as the entropy of the true latent variable h of z goes to 0. So the formal statement reads as follows. Let me define QP as the set of joint distributions which fit onto the latent graph for the observed distribution P. Okay, and again, let me sample the conditionals in the triangle graph from uniformly randomly from the corresponding dimensional simplices. Then, in the limit as entropy of C goes to 0, probability that I will sample a P of Z, probability that I will sample a P of XY from this triangle graph, such that I can construct a Z prime with entropy less than entropy of Z goes to 1. Sorry, such that I cannot construct such a Z prime goes to 1, which means that for almost all distributions, I can never find a simple enough Z prime that can make X and Y condition independent. This is true in the limit. Okay. Okay, so, okay, this statement is nice because you can actually show this is true irrespective of the support size of C. And this is exactly what we wanted. We wanted to say, oh, even though Z has large cardinality support size, maybe if its entropy is small enough, I can still recover the true causal graph, right? And this theorem, in the limit at least, it says that that's actually true. So now, one important thing to point out is that, for those who are interested, we are actually using a characterization of Kumarli and El-Gamal from 2014 in their paper titled Exact Common Information. Exact common information is a slightly different quantity, but they are using the exact same quantity that we are interested here, which is finding the simplest Z prime in terms of its entropy that can make X and Y condition independent, and they are using that to bound their quantity of interest. Now, they have a result for the binary variables, which basically a lower bound on how simple that latent variable can be to make P of X, Y condition independent, and we are actually using their characterization in this theorem. So one issue to extend this to general case where I have variables with larger number of states is that we don't have such a characterization in the literature as far as we are aware of that tells us what's the minimum entropy that I can construct a Z prime that can make X and Y independent. So this is not known as far as we know, so we cannot extend this because of that. Okay. All right. So, okay, this is true in the limit, but what happens when you have finite non-zero H of Z, right? So again, using the same characterization, we can actually very closely approximate this quantity, the fraction of identifiable models using this approach, by just sampling and averaging. And here, let's just focus on the blue curve, and that's what the theorem statement is. As you can see, even if entropy is not zero, let's say entropy is less than 0.1, still let's say 90% of the models are identifiable with this approach. And this is true in the binary case. So we are hoping that this is an indicator that it's going to be even more true in the case where I have more number of states for my observed variables. And I'm going to show some simulations about it later. Okay. All right. So in the general case, so one problem I have is that basically if I could find an algorithm that can construct the simplest Z prime, I still need a way to threshold this Z prime, right? So for this, we have a conjecture. So we assume that H of Z is small compared to minimum of H of X, H of Y. And then we have the following conjecture that says that, again, I have used the same sampling model for P of X, Y, Z, which means distribution is coming from the triangle graph. Then we believe there is a linear function on the H of Z that I can construct to make X and Y condition independent in terms of the minimum of H of X, or H of X, H of Y. So we have some simulation to support this, but we don't have a proof for the statement. Okay. So if this is true, then this gives us a way to threshold the entropy of the reconstructed random variable latent confounder Z to obtain to decide which causal graph is the true causal graph. Okay. So now we want an algorithmic approach again for this, right? When we use the entropy instead of cardinality. So for this, we can write the problem, but we are going to use a relaxation of the problem here. So I'm going to try to minimize H of Z subject to the constraints. And instead of writing the condition which information zero constraint, I'm going to relax it and say, okay, maybe if condition which information is less than delta, I'm going to still treat it as condition independent for practical purposes. So this is a relaxation of the problem. And using this, I'm going to take this constraint and I'm going to use it for regularizing my loss function to come up with the new loss function, which is condition mutual information plus beta times entropy of Z. So my objective is going to be to try to minimize this loss function. Okay. So now, instead of constructing Q of X, Y, Z, I'm going to construct Q of Z given X, Y, and I'm going to multiply it with P of X, Y to obtain Q of X, Y, Z. This basically is just a small trick to take care of the constraint that Q should marginalize to P of X, Y. Okay. Then I can write my optimization variables, Q of Z given X, Y for every X, Y, Z. And I can write my constraints, which basically imposes that each of these Q, Z given X, Y is a distribution. Okay. Now, one thing that we think is important for using this loss function is the following. We believe there is a trade-off between the complexity of the latent variable that we reconstruct versus the amount of dependence that it can explain away. So what I mean by this is the following. So suppose I'm trying to construct a Z that can make X and Y independent, right, condition independent. I can always use X itself, right, because X and Y are independent condition on X. It's not a very useful thing to do, but I can do that, right? But the problem is that the Z that I construct is going to be as complex as X itself. okay, maybe now I have an algorithm that can actually search over all Z's and find me a simpler Z with less entropy, which let me call this Z1, right? Z1 can still make X and Y condition independent. Now, if I try to further reduce entropy of Z, maybe I can find a Z2, but this Z2 cannot make them fully condition independent, but some dependence still remains, encoded by this weak edge you see here. This is the conditional mutual information between X and Y given Z2. And if I try to further reduce entropy of Z, let's say Z3, the conditional mutual information has to increase. If I use Z3 a constant, conditional mutual information will not decrease at all, right? So this little story tells us that probably there's a trade-off between the entropy of the latent variable or the simplicity of the latent variable versus the conditional mutual information, how much it can reduce conditional mutual information. Okay. So to understand this loss function, we basically identify and characterize the stationary points, and then we use this characterization and turn it into an iterative update algorithm. Okay. So this is the algorithm. I'm not going to parse it here. But it basically starts with some conditional, and it applies an iterative update algorithm until convergence or until a finite number of steps. And we have the following theorems about the algorithm, that the stationary points of this algorithm, which we call latent search, are stationary points of our loss function. And also that for beta equals 1 value, the specific loss function, latent search converges to either a local minimum or a saddle point. Okay. Again, I'm not going to parse the proof, but just going to show it here for reference. Okay, so let's see a typical use of our algorithm. So again, loss function is shown here on the right-hand side. And the loss function admits a beta value, right? This is a parameter. Now, you see here the mutual information and entropy plane. So x-axis is the conditional mutual information between X and Y given Z, and y-axis is entropy of Z. So each point that you see here is an output of the algorithm for the same input, same P of X, Y. As you can see, as I increase beta value, I will force entropy of Z to be smaller and smaller, but then I cannot make conditional mutual information as small as I could before. Right? So this output, this typical output, is an evidence that supports that there is a fundamental trade-off between entropy of Z versus how much conditional mutual information can reduce. Okay, so that was the algorithm for discovering the latent variable given P of X, Y. Now I can use this to actually come up with a causal inference algorithm that tries to distinguish between these two causal graphs. I'm not going to parse this algorithm here, but I'm going to give you a pictorial description of what it does. Okay, so the main weakness of this approach, of this whole approach, is the following, that I need two thresholds now. So the first threshold is a threshold on the conditional mutual information, below which I will deem these two variables as condition independent. And this may be easier to obtain. Let's say I say 0.005 is good enough for me, and below which I will say they are condition independent for practical purposes. But I also need a way to threshold entropy of Z that I construct, right? So I will use, in this case, in this picture at least, minimum of h of x, h of y as a way to threshold. And the region below these two lines is going to be the feasible region for me, which basically means the following. I will run my algorithm for different beta values to get to these dots, right, these outputs. And if I see any model, any point inside this green region, feasible region, I will say, oh, I could reconstruct a simple enough Z that could make the variables almost condition independent. That means it must be coming from the latent graph. Whereas if the output looks something like this, where no point falls into that feasible region, then I will say I couldn't find a simple enough Z, so that must come from the triangle graph. Okay, so this is how the algorithm works. And these outputs actually are exact outputs that you see when you randomly sample a distribution from this graph. This is what you get typically, that points lie much above the feasible region. And this is a typical output when you sample from the latent graph. So from simulations, it seems like this idea will work. Okay. So now I will give a synthetic simulation result. Again, I'm sampling distributions uniformly, each conditional uniformly randomly from the corresponding graphs. Okay, so let's just focus on the pane here in the middle. So each of the dots is a distribution, and each orange dot comes from the latent graph, and each blue dot comes from the latent complete graph. Okay, so the x-axis that you see here is the entropy of the true latent variable, which generates the distribution, and y-axis here is the entropy of the recovered variable when I use my algorithm to recover a Z, simple enough Z. Right? So as you can see, if the distribution is coming from the latent graph, the algorithm almost always constructs a z prime that has entropy less than equal to true entropy of the latent variable, which is shown here by these points lying below this y equals x line. Whereas if the distribution is coming from the complete graph or the triangle graph, then most of those points accumulate at the upper side of this graph, which basically means that entropy of the reconstructed variable cannot be made too small. Now you can see if I have an upper bound on the entropy of the true latent variable, let's say 3 bits, and here you see the accuracy based on this scatter plots, then for almost all distributions that I observe, I will be able to tell apart the causal graph, whether it's the latent graph or the complete graph or the triangle graph, right? There is an overlap region here, which basically says that, oh, if the entropy of the latent variable is this large, then I won't be able to distinguish these two causal graphs with this entropic approach. Now let's look at the graph on the right-hand side. So this is basically the same result, but I doubled the cardinality of the latent variable from 20 to 40. Each of the observed variables have 20 states, and the latent variable has 40 states. This is the setup I was more interested in. And even here, as you can see, even though the overlap region has increased, if I bound the entropy of the latent variable, let's say again 3 bits, then for most of the time, I will be able to tell apart the true causal graph. Okay? So this simulation is actually supporting what we suspected based on the theorem we had in the binary case, that this type of identifiability result extends to non-binary case, even though we don't have a theorem for it. Okay. All right, so this is the synthetic simulation. And the last thing I want to share is basically a result on the real data set. So this is called the adult data set, and it has discrete and categorical features like education, marital status. And the good thing is that they have many samples. And we can use these many samples to predict the probability distribution accurately. But the thing is that this is a larger causal graph. Now, what we want is basically, we want to use our approach, and we want to see if we can use our approach to discover the skeleton structure of the causal graph. What I mean by skeleton is basically the adjacency structure. If one of the two variables causes each other, then I will say they are adjacent. And if they are not, I will say they are non-adjacent. So that's the skeleton structure of the causal graph. Now, here's how I will apply the algorithm. I will look at every pair of variables, and I will run my algorithm, and I will look at the output. If the algorithm outputs a triangle graph, I will say, oh, I couldn't find a simple enough C to make them independent. Therefore, they must be adjacent. And if algorithm outputs triangle graph, that means I could find a simple enough C, then they should not be causing each other. Hence, I will declare them non-adjacent. And here you can see the results. As I mentioned before, it's very important how you threshold the entropy. And here we are using this particular thresholding scheme. But if we use this, you can see that the results are very similar to other methods, existing methods, which is, let's say, hill climbing algorithm here and PC algorithm here. So this you can see as a hyperparameter that you may need to tune depending on the data set. So we don't have a very good way of doing this right now. But one thing you can do is that if you have some idea of what causal graph should look like, you can search over all these thresholding mechanisms, and then you can stop when you think it looks reasonable enough, right? Because as you change this thresholding, the graph will either get denser or it will get sparser. And then there's a sweet stop in the middle that we don't exactly know how to stop there, but if you have some external evidence, then you may choose it properly. Okay, this is just a proof of concept that this may be used for discovering the adjacency structure of a causal graph. Okay, so that's all I had. If you have any questions, I'll be able to answer them, and thank you for listening.
Thanks a lot, Murat. So yeah, one question, maybe a big picture question. So maybe it's more like philosophical question about causality and correlation. So, and I mean, and maybe also, maybe if you can talk a little bit about application. So taking the example of smoking and cancer, whether there is a latent variable. So if I'm a doctor or if I'm a scientist, I mean, if I can know that there is correlation, isn't that enough? Why do I need to know whether it's causality or not?
So that's the thing, right? So as I said, so let me go back to those slides.
I mean, I know that if there, what I'm saying, maybe I'm being the devil's advocate. Once I know that if someone smokes, then very likely he or she is going to have a cancer, lung cancer. Isn't that enough?
No. So that's the thing, right? So you don't know that. You know there's a correlation, but that correlation may be because of a gene, right? So that's perfectly plausible. Now, you are going to tell this guy, oh, stop smoking and you will not get cancer. But if the true causal graph is the first one here, that's not going to be true.
One of the graphs it is.
Sorry?
Because you don't know which one of the two graphs that person is.
Exactly. So yeah, if you don't know the graph, then you cannot tell him to do something and expect an outcome, right? The outcome is really tied on what the causal graph is. So you might just say, if this is the true causal graph, then you can just enjoy your cigarette because it's not going to change anything about your cancer rate anyway, right?
But this means you need like lots of samples on one person, right, to be able to determine.
Oh, okay. So you are talking about the case where there may be different causal graphs for each person.
No, even for one person, right? I mean, how would you determine, like, if you look at your two data sets that you mentioned, the Tubingen and the adult, right? So they're concerning many individuals, right? Not a single one.
Right. You have many samples. Yeah. Each individual is a sample point for you.
Yeah, but then you're finding one graph that fits all of them.
Right. So that's the assumption, right? The assumption is that all of these samples are IID samples coming from the same causal graph. Yes, that's the assumption. I guess I didn't mention.
So basically, if I want, let's suppose there is data set concerning the slides that we see right now, which is the gene, the smoking, and cancer.
Mm-hmm.
You're sampling the data from the individuals, but you're trying to fit a single graph on all these individuals, but you don't know which one of these two graphs is the correct one.
Yeah, but if you assume that everybody has the same graph, no matter which one it is.
Oh, so you assume, okay.
That's the assumption, right? That's because every human body works the same way, let's say, or in a very similar way in terms of this.
Okay, so you're assuming that.
Right. So each point that you see or each person that you analyze is an IID data point for the causal graph that you are trying to learn.
But the causal graph is fixed.
Yeah, for the same causal graph that you are trying to learn. Yeah.
But then if I want to make predictions, like you were discussing before, is that I need to know what is your graph.
Right, but if I assume everybody has the same graph, then all I need to do is to learn that what graph is, right? What that graph is. Everybody has the same graph.
Oh, so you're saying if in the end it's the one with the upper graph, which is the one with the latent model, then you cannot tell the person stop smoking because it may or may not.
Yeah, it will not change anything. I mean, if this is a true causal graph, probably it will not change anything. So you can just tell him to enjoy, right? That's all. I mean, this is a weird example, but you can come up with examples where it will be catastrophic to suggest a policy if the causal graph is actually wrong.
So in terms of this specific example, does smoking cause lung cancer or not? I mean, what
it does. Yes, today we know that through other means by I guess people have analyzed the pathways and stuff. I'm not exactly familiar, but today we know smoking causes cancer.
Okay.
But back in the day we did not know, so this was a possibility.
Okay. Mm-hmm. And how I mean, again, maybe we're just digressing a little bit, but if it does cause, how come some people smoke without getting cancer?
No, okay, so this is not a deterministic relation, right? So this is a distribution.
Okay.
And if you are a smoker, you are more likely to get cancer, but not necessarily you will get.
Okay.
Right? So this arrow doesn't mean that you will. It's a deterministic relation. It's a conditional distribution, like you see here. If you force people to smoke, you will see zeros and ones, but ones will be more frequent than zeros. Whereas if you force people to stop smoking, you will see rarer ones, right? Rarer lung cancer instances.
Okay. All right. So I don't know if anyone else in the audience have questions. Okay, so if there's no more questions, people who watch the talk later on YouTube can maybe comment and then you can answer.
Yeah, that would be great. Any offline questions, just shoot me an email.
Sure. Yeah. Thanks a lot, Murat, for the interesting topic.
Thank you for the invite and thank you for listening.
Yeah.